Manage to relate to this is
All right, this is part three of our thermochemistry lecture. Part three. So make sure you go back and watch if you haven't done so. You watch part one and part two before you watch part three. Your homework is quest 19C. We are still on thermodynamics first law. 19C. So make sure you do 19A, 19B, and 19C. Now, we talk about four different ways to calculate delta H, enthalpy. We already discussed calorimetry. We discussed one version of Hess's law yesterday. Why don't we do one more on that version before we move on? So, given the standard heats of reaction, okay, so we have those reactions here. The question is, calculate the average bond energy for a single MX bond. Single MX bond. So they don't give us a target equation. Alright? So we need our MX4 to be on the reactant side and break it down into M plus 4x for MX4. MX4, break it down into M and 4x. But because they ask only for MX bond, if you have M, this is M, this is X4, this is X, this is X. They are asking only for MX. So when we find MX4, we need to divide it by 4 to get just 1 MX. So that means this is our target equation. So the problem here, if I did not tell you, it would be hard to know the target equation. So make sure you learn that. So let's see how we would do. I need the MX to be on the reactant side. MX on the reactant side. So I will go ahead and flip the first equation. If you would get your calculators ready for me, please. So this is MX4 gas. We said yesterday the state is important. Yield M. This is okay, M solid plus 2x2 gas. Because we flip that equation, the delta H is positive 148.7 kilojoule per mole. Alright? And then I need M and 4x. I need M gas on the product side, but this is an M solid. So I need to flip the third one. I cannot cross out here because as you see, I put an action here. I cannot touch it. So let's go ahead and flip the third one because that's why we said the state is very important. So I will flip this third one, which is M solid, yield M gas. Because you need to add energy to change from one state, from solid to gas. This is gas. And the delta H for this equation is positive. It is positive 30.1 kilojoule per mole. Let's see what else I should do. because I need, where's my target? I need 4x. I need 4x on the product side, and I see 2x on the product side here. I will multiply the second equation by 2. So it is x2 gas yield. It is 2x2. I said multiply by 2. 2x2 yield 4x gas. Because I double the equation, the delta H for this equation is, what is it? It is 684.6. 684.6 kilojoule per mole. Now let's see if I can do some cleaning. Change the color here. Let's see what we can change. This is M solid. This is M solid. What else? I have, I heard X2. X2. I have 2X2 here. I have 2X2. When you cross out, make sure they are in the same state. Same state. What else? That's all. So I can rewrite my equation. This is mx4, mx4 yield. This is mx4 yield m gas plus 4x gas, and delta H for that equation, you just add everything. So can someone give me the answer, please? 863.4 kilojoule per mole. But this is not the answer, because we said we need 1/4. They need the energy for only 1 mx. So we need to get that answer and divide by 4 to get for only 1 mx. The answer is 215.85 kilojoule. So this is the answer. Sometimes they will give you a sentence, they don't give you the target equation. You need to figure it out. Let's move on. Now, standard enthalpy of formation. If you check your textbook, in the back of your textbook, you will have a table for standard enthalpy of formation for different compounds. And of course, it's not a complete list. Alright, so let me tell you how to write the equation for a formation of a compound. So, let's say we chose NaCl. If they ask you to write an equation for the formation of NaCl, my advice to you is always draw the arrow, put that substance on the product side. And remember, you need to form only 1 mole. Always 1 mole from its elements in their standard state. Let me repeat. When they ask you to write an equation for the formation of a compound, you should always form 1 mole, always 1, and you should always have on the reactant side those elements in their standard state. Not polyatomic ions, not compounds. It has to be their elements in the standard state. And the element we have here is sodium, solid, that's the way it exists on the periodic table, plus this is Cl2. I don't write Cl, I write on Cl2 because Cl is a diatomic molecule. So you need to write those elements the way they exist in nature at 25 degrees Celsius, 1 atm. Because you should never change that 1. It should always be 1. The only way we can balance is to use a fraction right here. It is okay to use fraction on the reactant side, but you should always form 1 mole, nothing else. And it should always be from their elements. Let me choose another example. Unless someone wants to give me something. Let's go with aluminum phosphate. So I put my arrow here. I write down aluminum. Let me make it sulfate to make it more complicated. Sulfate is it Al2 This is SO4 3. You should never change that 1. It should always be 1. And then we should always use the elements. The elements are, this is aluminum solid plus, this is the only time I will ask you to split polyatomic ions. You do not use ions. Okay, it has to be the elements. So polyatomic ion, yes, break everything down. The elements are sulfur. Okay, and then the elements are oxygen. Oxygen gas is always O2. It is diatomic. Those are the elements. Now I will just balance without touching that 1. So I have 2 aluminum here, and I have 3 sulfur here, and they are 12 oxygen. I will put a 6 here. So students always make mistake. They want to change, they want to put a coefficient here. It has to always be 1. And then remember, those are elements in their standard state. Alright, let's move on. Now, this is a diagram you have in your textbook, and you should be able to explain it also, that show you the different steps for the formation of 1 mole of a compound, an ionic compound. Now, this is lattice energy. So you can write that in that definition. Lattice energy is the energy required to break apart an ionic solid and convert its component atoms into gaseous ions. Okay, the formation of 1 mole of an ionic compound. So you can go both ways. You can go with minus lattice energy. Instead of forming, you break down. So it can go both ways. To form 1 mole of an ionic solid from its gaseous ion, or to break down a mole of an ionic compound into its gaseous ion. One will be negative, the other one will be positive. Let's see the different energies involved. If we start, let's start right here. If you start with your sodium, this is sodium solid. The energy involved is you need to change that sodium solid into a gas. And from solid to gas, we'll call here delta H of sublimation. Solid to gas is the heat of sublimation. And then it says gaseous ions. So that sodium will have to lose an electron to become a cation. So the loss of electron is ionization energy. Okay, from Na gas to Na plus, the loss of electron. You need energy here, ionization energy. This is your chlorine. It is diatomic gas. Alright, you need to break it down. You need to dissociate it into just Cl, not Cl2, just Cl. And then that Cl will need to accept an electron to become Cl minus. That's what we call electronegativity. Okay? Or electron affinity. And then that cation in the gaseous phase, anion in the gaseous state, will get together to form an ionic solid. That's what we call lattice energy. What you need to know here is the different energies involved in the formation of 1 mole of an ionic compound in a solid. Okay, next. Here's the second version of Hess's law. We talk about the first version. Here's the second version. Those are the steps. This method is the simplest of them all. Number 1, underneath the reaction, write down the values that you find in the table in the back of your book. Okay? So Andrew will be checking the back of the book for us. Step 2, add up the products, multiplying the values by any coefficient. Don't worry about writing this because it's easier when we practice to see exactly what's going on. Step 3, add up the reactants, multiply any values by the coefficients. Step 4, do the calculation. All you need to remember, the formula for delta H of a reaction, okay, delta H RXN, and the reaction does not have X, but this is the abbreviation for the word reaction, equal, okay, standard enthalpy of reaction equal sigma, the sum of capital Greek letter, okay, the standard enthalpy of formation of the products multiplied by their coefficients minus the sum of the standard enthalpy of formation of their reactants times their stoichiometric coefficients. If I'm talking Greek to you, don't worry, because we are going to practice. You will understand what's going on. So let's start. Here's our first practice. If they ask you to find the enthalpy of this reaction, let me tell you in advance to warn you. Yes, I thank you very much for pulling out those calculators. The problem students have with this type of problem is not chemistry. It is not chemistry. It is the math. They are not very careful plugging the numbers on the calculator. So I'm warning you, you have to be extremely careful, extremely organized to enter those numbers. First, I am going to write my formula. The formula said delta H reaction equal. I would strongly advise you to write the formula before you plug numbers. On the AP exam, you get a point just showing your before you plug. Before you plug any numbers, please write down the formula. Delta H reaction equal the sum of the products are. Okay, let's go with the products. Let's go with, start with a bracket to organize everything. I'm going to write the standard. This is standard heat of formation of. I open parentheses. I'm going to get all my products. This is Al2O3. The coefficient is 1. I don't have to multiply by anything. Plus, open parentheses, the standard enthalpy of formation. I still have more products. It is AlCl3, close parentheses, have to be well organized, plus I have more products, 3 times coefficient, 3 times the delta H of formation of NO. Okay, close parentheses. I still have one more product, plus open parentheses, 6 times the delta H of formation of H2O. Close parentheses. I am done with the products. I close the bracket, minus open bracket, parentheses. The reactants are 3 times the delta H of formation of Al solid, close parentheses, plus open parentheses, delta H of formation of 3 times. This is 3 times. 3 times delta H of formation of ammonium perchlorate. It is NH4ClO4. Okay, close parentheses, and then I close the bracket. Let me repeat. Students have problem with this because of the math, because they do not organize all the numbers properly. And I already said you get 1 point in the AP exam for writing this before you plug any numbers. So make sure you do not just use your calculator and plug numbers. You need to set up this step. And then, now let me try to see if I can create space. Delta H of the reaction. Remember, all of those are formation equal. Now, since I'm plugging numbers, I don't really need bracket, but that's okay. You can use bracket. So that's why I need your help right now with the calculator, please. Let me use parentheses. So, what is the standard enthalpy of formation of La2O3? It is right here. This is negative. Be careful with the signs. This is 1676. I have to be very careful. That's the one I just put here. plus AlCl3. Keep an eye on me, guys, in case I make any mistake. AlCl3. It is negative. Okay, I can put negative here. Negative. This is 704. That's mean, let me use a bracket just to make sure. Use a bracket here. Negative 704. Alright, so I'm done with this one plus 3 times. 3 times this is, what is the other one? Is NO. Is that NO? Yes. This is our NO. It is 90. Close parenthesis. We still have one more. Plus 6 times the water. Where's my water? It is right here. It is, did I say 6 times? 6 times. Negative 242. Let's see who can give me that big. Let's continue. That big answer. Leave it ready for me, please. All of this. Now let's go with the second part. This is minus. We are here. 3 times the delta H of formation of just aluminum. Guess what? Listen carefully. The standard enthalpy of formation of any element in its standard state is 0. Alright? The standard heat of formation of any element in its standard state, the way it exists, is 0. So I have students scratching their head, going crazy, but they did not give me the standard enthalpy of formation of aluminum. I cannot do it. I don't have all the information. It is 0. They don't have to tell you that. They won't tell you. So it is, where are we? This is minus. I use another bracket. It is 3 times 0. Okay, 3 times 0. And then the only thing I have left here is my ammonium. Where are we? Yes, it is 3 times the delta H of formation of the ammonium perchlorate, which is negative 295. Okay, close my bracket because that's the only thing I have. Remember, the aluminum is 0. I'm going to see how good my dear students are in plugging those numbers. Okay, say that again. Negative 2,677. Great job. Great job. On every single test, if I have 10 students in that class, usually I have 10 different answers. Okay, so I'm so glad you can plug those numbers. This is delta H of the reaction equal to negative 2,677. Remember the unit, it is kilojoule. Kilojoule per mole. So you have to be extremely careful. Let me see, I think I have time for one more. Alright, so this is the second version of our Hess's law. So we already covered calorimetry. Okay, we already covered the first version of Hess's law. That's when you change the equation to get a target. We just covered the third version to get enthalpy. Let's see if it's a good way to start. I'm going to leave this here for a second, and I hope you check the problem. You pause the video. This is another way for you to practice to see if you have it right. Let me show you the answer to give you more confidence after you do it to see if you are right. Now, let me tell you the trick here in this problem. Let me close, write down the answer, pause the video. Let me tell you the trick here. Let me close. All right, I don't need to move this. I'm going to stop because I know it's getting too long. Let me quickly read the trick for you. Sometimes all values are not found in the table of thermodynamics data. For most substances, it is impossible to go into a lab and directly synthesize a compound from its free elements. The heat of formation of the substance must be found by working backwards from its heat of combustion. This is what happened here. This is the equation. This is your delta H of reaction. They gave you the delta H of reaction. And because it is on the product side, it means energy had been released. And because energy had been released, you need to write the delta H of the reaction as a negative number. Now you are going backward. You do exactly what I did, except this is your unknown. This is your unknown. It is the delta H of formation of that glucose. You are not solving for delta H of the reaction. It was given to you. Okay? So delta H of the reaction is negative 2800 kilojoule. You are solving for delta H of formation of one of the reactants. So I hope you complete this problem and to see if you have the right answer. Okay, I wish I could continue, but I know I promised I wouldn't go over 30 minutes for the video. So I will have to stop here. I hope you do your quest and then practice this problem. So enjoy the rest of your day.